that make every single piece of software tick. Let's jump in.
Have you ever just stopped and wondered how? How does Google Maps find you the fastest route, like instantly, even with traffic? Or how does Instagram load your feed so fast it feels like magic? Well, I can promise you it's not magic. The real secret, the magic sauce behind all that speed and efficiency, it really just comes down to one powerful, simple idea: organization. How data is structured behind the scenes, well, that changes everything. And that, my friends, brings us to the star of today's explainer, the data structure. At its heart, it's really just a special way of holding on to data. It's a container designed for a very specific job, to make sure information can be found, used, and changed as fast as humanly or, computerly possible. So where do we even begin with all this? Well, let's start with one of the most fundamental structures out there, the simple, straightforward line, or as we call it, a list. Okay, let's get the kind of textbook definition out of the way first. A singly linked list is basically just a series of items. We call them nodes. Each one of these nodes holds a piece of data. And, this is the important part, it holds a pointer that links to the next node in the chain. And this is the perfect way to picture it. Seriously, just think of a train. The first node is your engine. Each train car is a node holding its cargo, that's the data, and it's only connected to the one car right behind it. Simple as that. So you might be asking, okay, a train, I get it, but why? Why do it this way? What's the big deal? What's the advantage of this kind of setup? Well, the huge advantage here is flexibility. Adding or removing a car from the middle of this train, it's incredibly easy. But there's always a trade-off, right? Here's the catch. If you want to find, say, the 50th car, you have to start at the engine and walk through every single car, one by one, to get there. There's no jumping ahead. Let's actually see that in action. Here's our train of nodes, all linked up. Now imagine we need to slot a brand new car right into the middle of it. And just look at how simple this is. We don't have to tear apart the whole train and rebuild it. Nope. We just change two links. We unhook one connection, point it to our new car, and then hook our new car up to the next one in line. Two tiny changes, and boom, you're done. That's what we mean by efficiency. All right, so a straight line, that's simple enough, right? But what happens when your data isn't in a neat little line? What if it's hierarchical? For that, we've got to branch out and look at trees. Just like the name implies, a tree is all about hierarchy. Think about the file system on your computer. Folders inside of more folders, or a big company's org chart. Anytime you have parent items with child items, a tree structure is pretty much the perfect way to organize it. And here is a fantastic real-world example we can all get behind. A sports tournament bracket. Every match is a node. The two players are the children, and the winner moves up to become the parent of that node, climbing the tree until there's just one single champion at the very top. But here's the cool part. Just like in a real forest, not all data trees are the same. They're actually incredibly diverse, with all these specialized types, each one designed to solve a very specific kind of problem. So, for example, on the left, you've got that winner tree we just talked about. It's perfect for finding a single winner. But then you look over on the right, and that's an AVL tree. Its whole purpose in life is to automatically keep itself balanced. And why does that matter? Because a balanced tree means you can search for information in it at lightning speed. Okay, so we've gone from lines to branches. But what if the connections are just a total free-for-all? What if anything can connect to anything else? For that, we need the ultimate network structure, the graph. A graph is beautifully simple when you break it down. It's just a bunch of points, we call them vertices, and the lines that connect them, we call those edges. That's it. But believe me, from that incredible simplicity comes unbelievable power. A graph is the absolute best way to picture any kind of network. Think about it. On a social network, you and all your friends are the vertices, and the friendships between you, those are the edges. On a map, cities are the vertices, and the roads connecting them are the edges. And these connections, these edges, can have rules, which is really cool. An undirected edge, think of that like a friendship on Facebook. It's a two-way street. But a directed edge is more like following somebody on Instagram. It's a one-way street. You follow them, but they don't necessarily have to follow you back. And this brings us right back to our very first question. This is exactly how apps like Google Maps work. They see the entire world as one giant graph. Every intersection is a vertex, and every road is an edge. And those one-way streets? Yep, you guessed it. Those are just directed edges. The app's whole job is just to find the fastest path through that giant, complex graph. So we've seen lines, we've seen hierarchies, and we've seen these incredibly complex networks. All of this leads us to maybe the most important point of this entire explainer. Choosing the right structure for the job is one of the most critical decisions a developer can possibly make.
I love this quote because it just nails it. You wouldn't use a butter knife to chop an onion, right? It would be clumsy and slow. In the exact same way, a programmer won't use a simple linked list for a task that needs super fast searching. You gotta match the tool to the job.
So let's just boil it all down into a super simple cheat sheet. If you need a flexible sequence where things are added and removed a lot, think of a train. That's a linked list. If you've got hierarchy or you need to search really, really fast, think of a family tree. That's a tree. And for any kind of complex, interconnected network, think of a map. That's a graph.
These structures aren't just some abstract computer science concept. They are literally everywhere, hiding in plain sight. Now that you know what to look for, you're going to start seeing them. You'll see them in your music playlists, your YouTube recommendations, the very structure of the internet itself. The organization is all around you. Thanks for joining me on this explainer.